Welcome back! In this lesson we are going to learn about the parallel computing mode for Monte Carlo neutron transport simulations. Parallel simulations are getting very popular in the recent years because of the availability of parallel computing machines. So you may have a computer which has many cores within the CPU, the processing unit, or you may have a computer which has a multiple processors inside, or you may have access to a cluster of computers, or you may have access to a supercomputer in which you may have access to thousands of CPUs and cores. So naturally you may be interested in running your Monte Carlo simulation in a parallel mode. So when you run your simulation on two processors instead of one, you may expect to shorten the computing time by the factor of 2, and that is very often the case. However, how about when you have 1000 processors available to you? Will you shorten the computing time 1000 times? Well, it's not very clear. The answer to this question depends on what kind of problem you are trying to solve. The efficiency of the calculation may actually not scale linearly with the number of processors. So let's have a look at different problems that we may be trying to solve. So we have divided all the problems into two groups: the fixed source simulations and the criticality simulations. So let's have a look at the fixed source simulations first. Now, when you run a fixed source simulation on a single processor computer, this simulation actually represents a loop, and the steps within this loop represent the neutron histories. Now, the steps within the loop are actually independent of each other because these neutron histories are independent. We know the place at which the neutron histories start. So that is actually very easy to parallelize. Every time when you have a loop in which the steps are independent of each other, you can simply distribute the steps simulations to different processors. So when you, for instance, want to use 10 processors instead of one, you will simply allocate 10% of the steps to each single processor. So for instance, if you wanted to simulate 1000 neutron histories and you want to use 10 processors, we will simply allocate 100 of the neutron histories to every processor, and we run the independent simulations of these neutron histories on all those 10 processors, and at the end we just collect all the results and process it. So the parallelization of the fixed source simulation is really simple, and you can achieve a full utilization for all the processors that are involved in the simulation. Now, if you have a computer with 10 CPUs, you shouldn't expect that the computing time will be decreased 10 times, because there are some procedures that cannot be easily parallelized. For instance, you need to load the data library at the beginning of the simulation to the memory of your computer, and this you can't easily speed up. There may be some other factors that may slow down the simulation. For instance, the data transfer between the random access memory and the processors may represent a bottleneck for your simulation, and that often happens for neutron transport simulation because there is constant transfer of the cross-sections between the random access memory and the CPU, because the neutrons are colliding all the time. They are changing the energies, so new cross-sections are needed for the new energies. So when this happens, then the data transfer may limit the utilization for the processors. Simply, some of the processors have to wait till the data are delivered to them. However, these factors, they very much depend on the design of the computer. Let's have a look at the criticality simulations now. Unfortunately, unlike the fixed source simulations, the criticality simulations are more difficult to run in the parallel mode while maintaining a good efficiency of the simulation. And this is simply because the cycles within the criticality simulations are dependent on each other. The efficient source is dependent in each cycle on the simulations in the previous cycle. So we cannot simply split the neutron histories among the available processors because we simply don't know where they should start. So we have to simulate the first cycle first, we have to simulate the second cycle as a second cycle, and so on. We cannot jump over as we like. So when it comes to running the criticality simulations in a parallel mode, there are two major strategies. One of them is called the Masterslave scheme, and the other one is to run the independent parallel simulations. So let's have a look at the Masterslave scheme. In this strategy, we have a master CPU or a master process, and then we have a number of slave processes. So if we have 1000 processors, then we may allocate one processor to the master process and 999 processors to the slave processes. Now the master process is controlling the simulation, so it's distributing the neutron histories among the available slaves. So within each criticality cycle, all the neutrons that we want to simulate within the cycle are distributed among the available slave processors. At the end of the cycle, when all the processors are finished with the simulation of all the neutron histories that they were assigned, the new efficient source is collected again in the master process, and the efficient source is normalized, and it is again distributed into all the available slaves for the simulation of the next cycle. The second strategy simply executes the same calculation independently on all the available processors. However, it makes sure that the random number generator which is used in each of these calculations is using a unique seed for the sequence of the random numbers, so that different results are basically collected from all these simulations. So the benefit of this simulation is in reducing the random noise. So let's compare the advantages and the disadvantages of these two approaches. So let's have a look at the master-slave scheme first. So the advantage of the master-slave scheme is that the wall clock time needed for converging of the efficient source may be considerably reduced. This is simply because each of the inactive cycles is computed by all the available processors. So the actual wall clock time needed for simulation of a single inactive cycle is reduced because of this. The main disadvantage of the master-slave scheme is a typically poor CPU utilization, and this is because the processors need to communicate. So the communication takes place between the master processor and the slave processors, so that takes time. Moreover, we allocate approximately the same number of neutron histories to all the slave processors. Nevertheless, they may take different time to simulate them because the number of collisions of the neutrons within different neutron histories may be different. So you may really need different computing time to simulate different neutron histories. So it may happen that some of the processors will be finished quite quickly with the simulation of the assigned number of neutron histories, while some other processors may take a considerably longer time. So the master process has to wait till the last processor is finished with the simulation of the assigned neutron histories. So during this time, all those processors that were finished first, they have to wait till the last one is finished. So because of this, the CPU utilization may be very bad, especially when the number of the slave processors is quite large. So for a usual computer cluster, it is not recommended to combine more than 10 processors for a single parallel criticality simulation. Let's have a look at the other approach of simulating the independent parallel criticality simulations. The advantage of this approach is that the processors do not need to communicate with each other. Therefore, it is possible in principle to achieve a fairly large CPU utilization for this mode. Nevertheless, the disadvantage of this approach is that you need to converge the efficient source independently on each of these parallel calculations. Now, every cycle in each of these simulations is computed by a single processor. So it's going to take a long time until you converge the efficient source. So during the inactive cycles, basically the performance of this parallel simulation is identical to the performance of a single CPU calculation. The results would be pretty much the same. So if you are running the simulation on a very large number of processors, or if you are using a supercomputer, you are really wasting its computing time for these inactive cycles. So the real strength of this approach is when your efficient source is already converged at the beginning of the simulation. So it makes sense to converge the efficient source on your local computer and then use it for the parallel simulation on a supercomputer, in which case you can use this approach of running independent parallel simulations. On the contrary, if you want to use a computer cluster or a supercomputer for converging the efficient source, then it makes sense that you employ the Masterslave scheme for this purpose. So in a summary, I recommend that you use the Masterslave technique for the inactive cycles and the independent parallel simulations for the active cycles. So this is it. You have made it till the end. Have a nice day.